Assalamu alaikum everyone. My name is Farzina Abid and today I'll be discussing very exciting and important smart material which is known as iron gallium alloy. We commonly call it FEGA or galphenol. In this presentation, we will learn that FEGA alloy is what is why it is scientifically important and how its unique structure allows to convert mechanical energy into magnetic and electric responses. We will start by understanding its basic composition and crystal structure. Then we will explore its magnetorestrictive behavior, that is how this material changes shape when exposed to a magnetic field, and how it generates a magnetic signal when mechanical stress is applied. After that, we will discuss different processing methods, including conventional casting, rolling, and modern additive manufacturing techniques as laser power bed fusion. We will also see how FEGA alloys are used in real applications, especially when combined with triboelectric nanogenerators. Okay, and then finally we will briefly look at industrial considerations, sustainability aspects, and future research direction of FEGA based systems. By the end of this presentation, we will have a clear understanding of why FEGA alloy is considered promising smart material. Okay. Actually, I have divided the portion into three main portions. First, we have chemistry, crystal structure, and intrinsic physics of galphenol alloys. Okay, FeG alloys is also called galphenol. It is made by mixing iron with a small amount of gallium. Okay. This alloy is very important. Why? Because it shows high magnetorestriction. It is strong, tough, and easy to machine. It is useful for energy harvesting and zero power sensors. Okay. We will see the alloy compositions. Okay. uh, I gave you the introduction. First, now I'll talk about the different composition regions. 0 to 1 atomic percent gallium. Uh, Structure is almost pure iron. Magnetorestriction is very small here. Okay, when it's 10 to 20 atomic percent gallium, this is the best composition range. Magnetorestriction is maximum. Magnetoelastic coupling is very strong. 20 to 28 atomic percent gallium, atomic ordering starts to increase. Structure changes toward B2 and DO3 phases. Magnetorestriction starts to decrease. And if we have more than 28 atomic percent gallium, unwanted intermetallic compounds form like Fe2Ge4 and FeGa3. These phases damage magnetorestriction behavior. Okay, so for practical application, 17 to 19% is preferred. Okay, now we will see chemical and electronic structure effects. Gallium changes the electronic structure of iron. Main electronic effects: weakening of iron-iron interaction. What happens that Ga atoms replace some iron atoms. This makes the magnetic moments more easily to rotate. Okay. Change in density of state happens. Iron 3D bands become narrower. Gallium creates a small pseudo gap near the Fermi level. That is why it improves magnetoelastic coupling. Reduced magnetic anisotropy. Electrons become more localized near Ga atoms. Magnetocrystalline anisotropy decreases. Domain walls move more easily. Finally, even a small amount of gallium greatly increases magnetorestriction, does not significantly reduce magnetization. Okay. Crystal structure of FeGa alloy. It has a body-centered, we know BCC structure. Depending on Ga arrangement, three types of structures appeared. A2 structure disordered BCC. In this, gallium atoms are randomly placed in the iron lattice. This structure shows highest magnetorestriction, easy domain wall motion, and strong mechanical strength. This is the most desired structure for applications. And the next structure we have is the B2 structure, partially ordered. Gallium atoms in this structure start to occupy the specific lattice positions. Structural stability improves, restriction slightly decreases, usually after controlled heat treatment. Okay. Next we have DO3 structure, which is fully ordered. This structure is similar to Fe3Ga. Atomic order is very strong in this structure. Magnetorestriction becomes low because the domain walls cannot move freely. Internal stresses increase. The structure is not preferred in magnetorestrictive devices. Okay. Now we have a question that why atomic ordering reduces magnetorestriction. Okay, this is because when the magnetorestriction is high, when domain walls move easily, lattice is soft and flexible. DO3 ordering cause antiphase boundaries, internal stresses, strong domain wall pinning. Therefore, the heat treatments are designed to keep the alloy mostly in A2 structure and avoid excessive DO3 formation. Okay. Now we have the latest parameters, elasticity constants, and anisotropy. Lattice parameter for FeGa with about 20% gallium, lattice constant is 2.90 to 2.92 angstrom. Pure iron has a smaller value, which is 2.66 angstrom. Gallium size lattice increase, which reduces elastic stiffness, makes deformation easier. Okay. Elastic constants of FeGa alloy. Typical value for 17 to 19% gallium. C1 is 220 GPa, which is lower than pure iron and it allows easier deformation. C12 approximately 135 GPa, which controls shear behavior. C44, which is 120 GPa, it is slightly reduced and helps domain switching. Okay, now we have the overall effect. Lower elastic constant means less energy needed to create strain. Okay, like when the lower elastic constants are present, it means that we need less energy to create strain and there is higher magnetorestriction. And if we conclude overall things that we discussed above, we know that FeGa alloy is chemically simple but physically powerful. Small gallium addition greatly improves magnetorestriction and disordered A2 structure is the best one. Atomic ordering and intermetallics reduce performance. Soft lattice and low anisotropy enable strong magnetoelectric response. Okay. Now moving on to the next one, we have magnetorestriction physics in FeGa core depth. Now everyone, this is the heart of today's topic, so please focus carefully. We are going to understand why FeGa alloys shows such high magnetorestriction. Magnetorestriction in FeGa mainly happens because of 90-degree domain switching. Let me explain what this means. Inside the material, magnetic domains are already present. Each domain has its magnetization in a certain direction. Now, when we apply magnetic field, domains that are aligned with the field grow and domains at the 90-degree rotate and reorient. This 90-degree rotation produces a large strain in the lattice. Now remember, one important point, that is FeGa is dominated by the lambda 100 magnetorestriction coefficient. Okay. This means maximum strain occurs along the 100 crystallographic coefficient. Maximum strain occurs along the 100 crystallographic direction. Okay. For bulk single crystal FEGA, lambda 100 approximately equal to 250 to 200 to 400 parts per meter. Okay, this is extremely high for an alloy without a rare earth element. Okay. Now if we have two magnetic restrictions in a sorry two magnetorestriction peaks in FEGA. Now, this is very interesting and very exam important concept. Experimental studies show two magnetorestriction peaks in FEGA alloy. First peak is around atomic 19% GA. This is the main and the most useful peak. Okay. At this composition, delta lambda 100 reaches about 400 ppm. Microstructure is mostly A2 disordered. Domain walls move very easily. That is why most practical FEG devices use 17 to 19% gallium. Second peak. Okay. Now around the 27 atomic percent GA. At this composition, magnetorestriction is lower. Atomic ordering increases. DO3 structure starts forming. Even though magnetorestriction exists, it is less useful due to increased domain pinning, higher internal stress. So please remember this carefully, that the first peak is for higher performance and the second peak is order related lower performance. Okay. Now we're gonna discuss about magnetocrystalline anisotropy in FEGA. Now let us talk about magnetocrystalline anisotropy, which is denoted as K1. For FEGA, K1 is approximately equal to 2 to 8 into 10 is to power 4 joule per meter cube. This value is much lower than many magnetic materials. Okay, now let's see why is K1 important. Because K1 is important because magnetic moments rotate easily. Less magnetic field is required. Magnetorestriction occurs at a low excitation. So K1 leads to high sensitivity, low power requirement. This is very important for zero power sensors. Now we will discuss about domain wall motion in FEGA. Gallium improves domain behavior in three main ways. Let us discuss these three main ways. First is domain wall energy decreases. Walls move easily. Pinning centers reduce, less resistance to motion. Reversible 90-degree switching becomes possible and high frequency response is there. That is why FEGA works very well in high frequency sensors and harvesters. Now we have thermodynamics and phase diagram insights. Important features of FEGA phase diagram. Now let us look at the thermodynamic side. The FEGA phase diagram shows solution exists up to 30% gallium. Atomic ordering depends upon the temperature, and the ordering temperature B2 ordering starts around 600 to 700 degrees C. DO3 ordering starts below 550 degrees C. Okay, so temperature control is extremely important. Okay, from this data we know that the temperature control is extremely important. Now we will discuss the effect of heat treatment. Heat treatment strongly controls magnetorestriction. Quenching from 800 degrees Celsius retains A2 disordered structure, gives highest magnetorestriction. Annealing at 400 to 500 degrees C, limited DO3 ordering, moderate magnetorestriction. Long annealing at 350 to 450 degrees C gives excessive DO3 ordering, severe drop in lambda 100. Now we will see magnetic phase transition. Now let us talk about Curie temperature, which is Tc. For FeGa, Tc is approximately equal to 700 degrees C for compositions below 20% gallium. As Ga content increases, Tc slowly decreases. Okay, why is high Tc important? Okay, we'll find why is Tc important. Materials, because materials remain magnetic at high temperature, so stable under thermal fluctuation. This is excellent for energy harvesting in sensors. Okay. Now we have the mechanical properties and their importance. Mechanical robustness. Now let us compare FeGa with rare earth magnetostrictive materials. Unlike brittle materials like terphenol D, FeGa has high ductility, high strength, good fracture toughness, and their typical values are tensile strength 500 to 550 MPa, yield strength 320 to 350 MPa. Okay, this means that FeGa can survive real world conditions as mechanical shocks, continuous vibration, long term fatigue loading. What is fatigue behavior? FeGa shows low fatigue sensitivity, stable strain output over millions of cycles, internal friction Q inverse remains low. Okay. This is very important when FeGa is combined with tank system because energy conversions remain efficient, mechanical losses are minimum. Now we have thin film versus bulk FeGa. In thin films are less than 50 nanometer. Magnetoelastic coupling increases. Substrate strain can control anisotropy. Very small magnetic fields are sufficient. This allows extremely sensitive low voltage sensors. Okay, now we have bulk single crystals. Bulk single crystals show highest lambda 100 values, very precise strain response, and which are used in precision actuators, laboratory reference devices. Next is the polycrystalline FeGa. Polycrystalline materials show low magnetostriction due to grain averaging. However, performance can be improved by texturing, rolling, annealing, directional solidification. Okay. Defect chemistry and internal stress. Now we see what are the type of defects. Common defects include vacancies, dislocations, grain boundaries, antiphase boundaries, gallium clustering. What is their role in magnetorestriction and what is their effect on magnetorestriction? Antiphase boundaries strongly pin domain walls. Okay. Grain size affects coercivity and permeability, so defects must be carefully controlled. Now we have their roles in sensors and energy harvesters. For tank and cell powered sensors, we want low coercivity, like we need low energy input, high permeability, strong responses, low internal friction, high efficiency. If we see the quantitative summary, now let us quickly go through the important numbers. Magnetostriction value is 100, lambda 100, 250 to 400 ppm, very high. For non-rare earth alloy, saturation magnetization, which is 1.6 to 1.75 Tesla, strong magnetic response, coercivity 20 to 60 A by M, easy domain switching, Curie temperature 700 degrees C, excellent thermal stability, elastic modulus 80 to 180 GPa, softer than pure iron, tensile strength 500 to 550 MPa, mechanically robust, electrical sensitivity 20 to 25 micro-ohm centimeter, moderate eddy current losses. Okay, so everyone, FeGa alloy is a rare combination of magnetic, mechanical and thermal stability. Keep in mind these three things: magnetic, mechanical and thermal stability. Its high magnetorestriction, low anisotropy and strong mechanical properties make it ideal for modern technologies like triboelectric energy harvesting and zero power sensors. Okay, in the next part we'll connect this material directly to tank working mechanism and self-powered sensing systems. Okay. Now, deep reasons why FPGA is used in TENS and zero power sensors. Alright everyone, before we move fully into the manufacturing, let us pause for a moment and understand why FPGA is so special for triboelectric nanogenerators and zero power sensors. I mentioned two things: triboelectric nanogenerators and zero power sensors. Everything we studied so far, magnetorestriction, domain motion, low anisotropy, mechanical strength, now comes together. Reason 1, magnetomechanical transduction. First reason is magnetomechanical transduction. FPGA can convert mechanical vibration into magnetic change and also convert magnetic excitation into mechanical strain. This two-way coupling is extremely strong in FPGA. Okay, so in TENS and sensors, tiny vibrations, domain switching into electrical signal. No external power is needed. The second reason is sensitivity to nanoscale strain. Second reason is sensitivity. Okay, FPGA responds to very small strains even at nanoscale. Why? Because low magnetocrystalline anisotropy, easy domain rotation and high lambda 100 coefficient. This means even weak human motion, environmental vibration, structural bending can be easily detected. Okay, the reason 3 is low power magnetic actuation. Third reason is low power requirement. Okay, because coercivity is very low, magnetic movements rotate easily, so very small magnetic fields can produce measurement strain, perfect for zero power or self-powered sensors. Okay, now reason 4 is integration with flexible substrates. Fourth reason is mechanical compatibility. Basically, unlike brittle materials like FPGA is ductile, it can be rolled into thin sheets, can be bonded into polymers. This allows flexible tank devices, wearable sensors, structural health monitoring system. Reason 5 is high durability under vibration. Fifth and final reason is what? Durability. FPGA can withstand millions of vibration cycles, maintain stable output, resist fatigue failure. This is critical for long life harvesters, real world sensor deployment. So these 5 reasons clearly explain why FPGA is preferred over many other magnetostrictive materials. Now in portion 2, synthesis, processing, microstructure, control and manufacturing. Now everyone, let us move to the portion 2. Here we will see how FPGA is actually made, processed and scaled up for real devices. So we have a little overview of manufacturing routes. FPGA can be produced using several routes. Conventional metallurgy, okay, single crystal growth, thermomechanical processing, rapid solidification, additive manufacturing. Okay, but remember, final properties depend more on processing than chemistry alone. First we have feedstock and alloy preparation, raw materials and stoichiometry. We always start with raw materials. For high quality FeGa, iron purity should be greater than or equal to 99.9%. Gallium purity should be greater than 99 to 99%. Typical target compositions are Fe83Ga17 and Fe81Ga19. These compositions balance high magnetodestruction and good manufacturability. Okay. One important practical issue you must remember here is that gallium can evaporate and segregate during melting. So small devices which are less than 0.5% are expected. Engineers compensate during charge calculation. Okay. Now we have melting and homogenization. Common melting methods are arc melting, vacuum induction melting, or induction melting under argon. Melting temperature should be typically 1400 to 1550 degrees Celsius to ensure uniform composition. Melt and flip cycle at least 3 times. Okay. After melting, cast into ingots. Prepare for homogenization. Homogenization annealing. Temperature should be 900 to 1000 degrees Celsius. Time should be 12 to 48 hours. Atmosphere should be inert or low oxygen. Purpose is to remove the chemical segregation, dissolve unwanted intermetallics. Okay. Next point, we have bulk solidification and single crystal growth. Bridgman and Zocher-Lacy growth. Now let us talk about single crystals. Single crystals are grown because they show the highest magnetostriction and they have no grain boundaries to pin domains. Vertical Bridgman method. Slow translation 0.5 to 5 mm per hour. Strong thermal gradient, controlled cooling to avoid GA segregation. Okay. And the second method, pulling rate is 1 to 10 mm per hour and the controlled rotation atmosphere control is critical. After growth, cool it down very slowly, cut it into crystals, orient them along 100 directions. Okay. Now we have trade-offs of single crystals. Advantages are lambda 100 up to 400 ppm, excellent domain mobility, and the disadvantages we got is that it is very expensive, time consuming, and it is very limited in size. So single crystals are mainly used in research, precision actuators. Now we have the polycrystalline processing or thermomechanical routes. We have rolling and texture development. Okay. For large scale production, we mostly use polycrystals. Okay. Goal is to create 100 texture, mimic single crystal behavior. What are its process steps? First, we hot rolling at 100 to 800 to 1000 degrees Celsius. Cold rolling 20 to 80% reduction. Recrystallization anneal 400 to 800 degrees Celsius. Okay. Stress annealing during annealing. Stress annealing. Apply anaxial stress. Few megapascal to tens of megapascal effect. Preferred grain growth. Induced magnetic anisotropy, used specially for bending mode energy harvesters. Grain size control. Typically, grain size is 10 to 50 micrometer. Smaller grains are higher in coercivity. Larger grains are lower in coercivity. Better low frequency response. So grain size is optimized based on device design. Okay. Now next we have rapid solidification and melt spinning. Okay, what is the process of melt spinning? In melt spinning, molten alloy is ejected into a rotating copper wheel. Okay, and its key parameters are wheel speed should be at 15 to 40 meter per second, ribbon thickness should be 20 to 50 micrometer, and atmosphere should be argon. Okay, what are its advantages? Advantages are that very fine microstructure, suppressed atomic ordering, high potential magnetostriction. Applications are in sensor ribbons, feedstock for power. Okay, post spinning annealing. After spinning, anneal at 300 to 500 degrees Celsius times 5 to 60 minutes. Purpose is to relieve internal stress, avoid excessive DO3 ordering. Long anneals must be avoided. Next is additive manufacturing, laser power bed fusion. Why additive manufacturing? Now this is a very modern and important topic. LPBF allows complex shapes, lattices, centimeters, rapid prototyping. Powder requirements. Powder must be spherical. Particle size should be 15 to 45 micrometer. Low oxygen less than 0.1%. This ensures good flowability, minimal oxide defects. Typical LBPF parameters. Common ranges are laser power 15 to 400 watt, scan speed 400 to 1200 millimeter per second, layer thickness 20 to 50 micrometer, head spacing 0.06 to 0.12 millimeter. Okay, energy density must be optimized. Too high leads to GA evaporation and too low leads to lack of fusion. Target is density greater than 99%. Okay, post build heat treatment. After printing, stress relief anneal at 300 to 600 degrees Celsius. Duration 1 to 4 hours. Magnetic field annealing. Apply magnetic field during anneal. Field range should be 0.1 to 10 Tesla. Effect strong texture development. Lambda can increase 2 to 5 times. Okay. Now we have resulting microstructures. LPPF part shows fine dendritic structures, residual porosity, possible GA segregation. So post processing is critical. We know that post processing is more critical than the process happening itself. We have magnetic field annealing and stress field annealing. Magnetic field annealing purpose is to induce an uniaxial magnetic anisotropy, align easy axis, reduce drain domain pinning. Procedure is anneal at 300 to 600 degrees Celsius. Apply DC magnetic field. Time should be 30 minutes to 10 hours. Industrial field is 0.1 to 1 Tesla. Okay, procedure was this. High field labs in high field labs we use up to 20 Tesla. Okay. Now next we have stress annealing. Purpose is to couple mechanical and magnetic anisotropy. Typical conditions are stress few MPa to tens of MPa, temperature 350 to 500 degrees Celsius, time 1 to 10 hours, used widely for bending mode sensors, high repeatable devices. Okay, now we have combined MFA and SA. Finally, combining both gives the best results. Benefit is lowest coercivity, highest low field magnetostriction, excellent repeatability, used for final device tuning and high performance harvesters. So in final closing, everyone, FPGA is not just a material. It is an engineered system. Its chemistry, processing, heat treatment, and domain engineering all work together to produce exceptional performance in triboelectric nanogenerators and zero power sensors. Okay. Now we have thin film deposition techniques for MEMs and microsensors. Everyone, until now we mostly talked about bulk FPGA materials, but for MEMS devices and microsensors we usually need very thin films. So let us now discuss how FPGA thin films are made and controlled. Common thin film deposition methods. First, we have sputtering, DC or RF magnetron sputtering. The most commonly used method for FPGA thin films is sputtering. In sputtering, a FPGA target is bombarded with ions. Atoms are ejected and deposited on a substrate. Typical conditions are substrate temperature 200 to 600 degrees Celsius, base temperature below 10 raised to power minus 6 torr. Why sputtering is popular? Because its thickness, good thickness control. It has good thickness control, uniform films compatible with MEM's fabrication. DC sputtering is used for conductive targets. RF sputtering for better composition control. Okay. Pulsed laser deposition, PLD, is mostly used in research. Okay, in PLD, a high energy laser hits a FPGA target. Material is transferred to the substrate, and its advantages are excellent stoichiometry control, good for textured or epitaxial films. Its limitations are small area deposition, not suitable for large scale manufacturing. Okay. Next, we have molecular beam epitaxy, MBE. MBE is the most precise method but also the most expensive one. Okay, its features are atomic level control, ultra high vacuum, ideal for epitaxial growth, used mainly for fundamental research studying interface effects. Okay, effects of thin film thickness. Now let us talk about thickness, which is extremely important. Typical FPGA film thickness is about 220 to 200 nanometers, used in magnetoelastic MEMs, microscale sensors. As thickness changes, properties changes. Thin films, single domain behavior. Thicker films are used for multi-domain structures. Substrate clamping effect. Okay. Substrate clamping effect. One very important issue is substrate clamping. When FPGA is deposited on a rigid substrate, the substrate restricts free strain. Magnetostriction appears reduced. How do engineers solve this problem? They solve it by pattern released structure. They pattern the released structures using compliant substrates, micro machining, cantilevers. This allows the film to deform freely. Okay. Post deposition treatments. After deposition, films are not ready yet. They have residual stress, defects, and poor magnetic anisotropy. Okay. Rapid thermal annealing. RTA. Typical RTA conditions are temperature 300 to 600 degrees Celsius, short time exposure. And what are its effects? Stress relaxation, improved magnetostriction, and better domain alignment. Sometimes annealing is done under a magnetic field. This induces preferred magnetic direction, improves low field responsive, and oxygen control is very important. Okay, because FPGA oxidizes easily. Oxides reduce magnetic performance, so annealing is done in vacuum and inert gas. Okay, characterization and quality control. Now that we have fabricated the material, we must verify its quality. We are going to verify the quality of the material. Chemical and compositional quality control. Composition verification methods are ICP, OES, and XRF, and its purpose is to confirm gallium content within the 0.28%. This is critical because small composition changes strongly affect magnetostriction. Elemental mapping methods are EPMA and EDS. They are used to detect gallium segregation, find intermetallic inclusions. Now we have microstructural quality control. Microscopy is done using optical microscopy SEM, and these are done to detect porosity, cracks, grain size, dendritic structures. Electron backstacker diffraction, EBSD, electron backstacker diffraction, is very important for FPGA. It tells us grain orientation, texture strength, and its target is 40% grains oriented along 100 direction. This gives high effective magnetostriction. Electron backscatter diffraction has a main purpose of orienting almost 40% of grains towards 100 direction. Now we have magnetic and functional testing. Magnetic measurements are done using VCM squid magnetometer, and it measures MH loops, coercivity, and permeability. Magnetostriction testing. Special rigs measures lambda versus magnetic field, lambda versus applied stress. Condition must match real device operation. Dynamic and fatigue testing. This is extremely important for sensors, and its tests include cyclic loading 10 raised to power 6 to 10 raised to power 8 cycles, measures drift in lambda, check coercivity and stability. Non-destructive evaluation, NDE. Ultrasonic testing is done and it's used for bulk materials, detect internal cracks or voids. X-ray computed tomography, CT, used especially for LPBF parts, and it detects, what does it detect? Porosity, lack of fusion, internal defects. Typical process flows and protocols. Now let us connect everything into real process flow. High performance single crystal research scale. Now let's see the steps. Melt high purity Fe and Ga. Grow single crystal using VB or CZ. Orient along 100 directions. Stress relieve at 600 degrees Celsius. Magnetic anneal at 400 to 600 degrees C under 1 to 5 Tesla. Final polishing and QC. Device grade polycrystal sheet industrial, and its steps are: melt and cast ingot. Second, homogenize at 900 degrees Celsius, quench. Number 3, you have to roll, hot roll and cold roll. Number 4, crystallization with stress anneal. Number 5, magnetic field anneal 0.1 to 1 Tesla. Final cutting and QC. Okay, last point. Okay, now common defects. LPBF prototyping and post processing. Its steps are: produce spherical powder first. Second, print with optimized energy density. Number 3, stress relieve at 300 to 500 degrees Celsius. Number 4, HIP if needed. Number 5, magnetic and stress annealing. Number 6, final QC, CT, EBSD magnetostriction. Next we have common defects, failure models, and mitigation. Gallium segregation and intermetallics. Cause: slow cooling, poor homogenization, and its solution is to extended annealing and controlled cooling. Excessive DO3 ordering cause long anneals at intermediate temperatures. Solution: quenching, short anneals, magnetic or stress anneals. Porosity: LPBF parts It causes low energy density, gas entrapment, and its solution is to optimize printing parameters, use HIP, improve powder quality. Okay. Oxidation and surface contamination. Its cause exposure to air, poor powder handling, solution is inert atmosphere, use glove boxes, protective coatings. Okay. Now, so everyone's successful FPGA devices are not achieved by chemistry alone. They require precise control of processing, microstructure, defects, and domain behavior. Only when all these steps are optimized can FPGA deliver high performance in MEMs, tanks, and zero power sensors. Okay. Now we have scale up and industrial considerations. Scale up and industrial considerations. Up to now, we have discussed FPGA mostly from a scientific and laboratory point of view, but a material is only truly successful if it can be produced at a large scale, safely and at reasonable cost. So now let us talk about what happens when FPGA moves from the lab to the factory. Cost drivers in FPGA production. Gallium cost and availability. The first and the most important cost driver is gallium itself. Iron is extremely abundant and cheap. Gallium is much less abundant. Gallium is often obtained as a byproduct of aluminium or zinc refining. This means that GA price fluctuates strongly. Supply can be unstable. Okay. Why does this matter for FPGA design? Because FPGA magnetostriction is highly sensitive to GA content. Wasting GA during processes directly increases cost. Therefore, industrial design must consider high GA yield, efficient scrap recovery, minimal oxidation loss, single versus polycrystalline cost comparison. Okay, now let us compare different productive routes. These routes are vacuum controlled atmosphere furnaces, long growth times, millimeter per hour, very high operating expenses, OPEX, very high energy consumption. Okay. Advantages are high magnetostriction, best performance. Disadvantages are very expensive per kg, not suitable for mass production. Polycrystalline rolling route, casting, rolling, annealing, much cheaper per kilogram. Uses standard steel processing infrastructure. Okay. Advantages are good mechanical properties, scalable, cost effective. That is why most industrial FPGA components are polycrystalline. Additive manufacturing economics. Okay. Additive manufacturing changes the equation. Okay. Now I'll tell you why. Because it has high capital cost, machine, CAPX. Powder preparation is very expensive, but it enables complex geometries, reduces assembly steps, integrates multiple functions into one part. So higher upfront cost, lower system level cost for complex devices. Now we have environmental and safety considerations. No industrial material can be adopted without safety and environmental compliance. Handling of gallium. Gallium has some unique behaviors which are low melting point, can wet and penetrate many materials, can embrittle certain metals. Therefore, containers must be compatible, avoid prolonged contact with aluminium or some steels. Okay. Healthy and safety concerns. Some gallium compounds can be toxic. Metallic gallium is generally safe but must be handled properly. Required measures are standard metal handling PPE, gloves, eye protection, good ventilation, powder handling risk. Powders are always more dangerous than bulk metal. Its risks are airborne particulates, okay, inhalation hazards, dust explosion risk, fine powders. Controls: inert atmosphere, local exhaust ventilation, dust collection systems, waste and regulatory compliance. GA containing scrap is considered controlled waste in many regions. Disposal must follow local hazards waste regulations. Best practice is to treat scrap as a valuable recyclable material, not waste. Okay. Now we have supply chain and recycling strategy. Recycling FEGA scrap. The good news is that FEGA recycling is relatively easy. Scrap can be remelted, homogenized, and used. This includes meshing chips, off-spec parts, powder leftovers. Gallium loss issues are that main loss mechanisms, oxidation at high temperature and evaporation during melting. Vegetation, controlled atmosphere melting, protective slag or flux, short melt times, closed loop recycling. Modern manufacturing preferred closed loop systems. Closed loop recycling means scrap is collected, composition is monitored, material is reused internally. This reduces cost, stabilizes composition, improves sustainability. Okay. Now we have recommended characterization metrics for device production. Finally, let us talk about quality control because no device survives without QC. This is not just testing, this is risk management. Entry quality control, incoming materials, chemical composition verification. At the start, ICP, OES or XRF confirm GA atomic percent tolerance, very tight, typically 0.2 at percent. Oxygen content, especially for powders. Oxygen increases brittleness. Oxygen reduces magnetic response. Therefore, oxygen analysis is mandatory for powders. Okay. Intermediate quality control during processing. It happens microstructural inspection using optical microscopy SEM to detect porosity, cracks, homogeneous grains. Texture management is done using EBSD and it is checked fraction of 100 oriented grains, grain size distribution. This directly predicts final magnetostriction performance. Next we have mechanical screening. Hardness testing detects over ordering, excessive brittleness, improper heat quality. Functional quality control is done using VSM, Meyer hysteresis loops, coercivity, saturation, magnetization, magnetorestriction testing, critical tests, lambda versus magnetic field, lambda versus applied field. Dynamic fatigue testing. This is essential for energy harvesters and sensors. Cyclic loading up to 10 raised to power 6 cycles or more. Monitor drift in lambda, change in coercivity, mechanical degradation. Final quality control, non-destructive testing for bulk parts. Ultrasonic inspection, X-ray, CT. For complex geometries, detect internal cracks, porosity, lack of fusion. Device level testing for harvester and sensors, coil and load testing. It measures power output, frequency response, stability over time. This confirms the material work as part of a system, not just alone. So, FEGA is not just a smart material, it is manufacturable smart material. Its success comes from balancing performance, cost, safety, and reliability. Only when material science, processing science, and quality control work together can FEGA be deployed in real industrial sensors, MEM devices, and self-powdered systems. Okay, now we have portion 3. Technology, device design, and functional principles of FEGA galphenol in TENG, energy harvesting and zero power sensors. Now students, in this portion we will move from material science to real technology. We will see how FEGA, also called galphenol, is actually used inside devices such as triboelectric nanogenerators, energy harvesters and zero power sensors. Okay. FEGA is a magnetostrictive alloy, which means when we apply mechanical strain, it changes its magnetic state. Because of this unique property, FEGA can convert mechanical energy into magnetic energy, work together with triboelectric nanogenerators. Okay, so FEGA becomes a multifunctional transduction code. Why FEGA is important in modern devices? Modern electronics demand three things: very low power, very high reliability, very strong mechanical durability. FEGA satisfies all three. That is why it is increasingly used in hybrid energy harvesting. It is used in self-powdered sensors. It supports zero power electronics. Okay. Operating principles of FEGA in hybrid TNG systems. Magnetoelastic effects, the core principle. Let us first understand how FEGA works. FEGA operates through magnetoelastic effect. This means when FEGA is bent, stretched or compressed, its magnetic domains rearrange. This rearrangement causes a change in magnetic flux. This flux can be converted into electrical signals. Okay? Combination with triboelectric effect. Now when we combine FEGA with the TNG produces electricity through contact and separation of surfaces. FEGA produces electricity through strain-induced magnetic change. So now two energy conversion mechanisms work together. This is called hybrid transduction. Why this hybrid system is powerful? FEGA has a magneto restriction value lambda 100 approximately equal to 200 to 400 pm. This means that even small vibrations and even low frequency motions can produce a strong response. As a result, hybrid TENGs work well in the real environment where vibrations are irregular and slow, which is less than 200 Hz. Okay, effect on TENG performance. When FEGA is bonded below or inside the TNG structure, then mechanical bending produces triboelectric charges. At the same time, it produces magnetic flux variation. This increases output voltage, increases current, increases charge density, especially in vibration dominated systems. Okay. Second is advanced device architecture using FEGA. Bending mode hybrid TENG galphenol devices. This is one of the most common designs. Structure is FEGA strip bonded to polymers like PTFE, PDMS, Kapton or FEP. It's working. When the device bends, FEGA undergoes magnetostriction. Triboelectric layers separate and contact, and the result is larger contact area change and high surface charge generation. Okay. Second is cantilever type hybrid nanogenerators. In this design, FEGA is placed inside a cantilever beam. Okay. It's placed inside a cantilever beam. When the cantilever vibrates, FEGA produces magnetic flux changes. Coils or magnetic sensors detect this flux. Triboelectric layers generate surface charge, and its benefits are dual mode energy output, real-time frequency detection, and high sensitivity to small vibration. Number 3 is impact mode hybrid generators. FEGA is placed below triboelectric films. When impact occurs, FEGA experiences high strain. Magnetorestrictive response becomes non-linear, and this causes large voltage spikes, high power pulses. Applications are in wireless signal transmission, fast event detection. Okay. Number 4 is stacked triboelectric magnetostrictive arrays. Its structure is multiple FEGA layers alternating triboelectric surfaces. Advantages are harvest energy from multiple directions, synchronized domain rotation, higher overall power output, Number 5 is femtojol sensing platforms using FPGA films. Okay. Thin films, FPGA films are used in MEMS, micro TENG devices. This produce very small but stable signals which are suitable for IoT devices, biomedical patches, micro monitoring systems. They operate with zero external power. Next, we have performance characteristics and enhancements. Magnetostrictive response and efficiency. FPGA shows strong response at low magnetic fields, best composition, FE8 GA19. Performance is enhanced by magnetic annealing and stress annealing. These processes align magnetic domains, increases signals to noise ratio. Okay. Frequency dependent response. Triboelectric output increases with frequency. FPGA response stronger even at low frequency. Combined systems harvest energy over a wide frequency range. Stability and durability. Unlike brittle materials like terphenol D, FPGA is mechanically tough. It can withstand continuous vibration, repeated bending, and 10 to the power 7 to 10 to the power 8 cycles. This marks it ideal for industrial monitoring, long-term deployment, voltage and power enhancement. Experimental studies shows voltage increases by 2 into 10 power. Power density increases by 3 to 12 times compared to standalone TENGs. Also, output is more stable under humidity changes. Zero power sensing using FPGA TENG systems. What is zero power sensing? Zero power sensing means this sensor does not need a battery. It uses energy from the environment. FPGA enables this because it produces detectable signals without amplification. Structural health monitoring. Hybrid sensors detect cracks, load changes, beam deformation, vibration patterns. Okay. FPGA identifies deformation modes. TENG measures event intensity. Human motion and biosensing. Flexible patches detect joint motion. Okay. Analyze guide. Sense muscle vibration. Signals can be directly processed by ultra low power circuits. Okay. Passive wireless sensing. FPGA modulates magnetic or RF circuits combined with TENG enables wireless data transmission without batteries. Environmental and vibrational monitoring. It is used for machinery monitoring, railway tracks, flow sensing, pressure variation detection. High fidelity comes from combined magnetoelastic and triboelectric effect. Okay. Number 5, we have integration techniques and interfaces. Bonding FPGA with triboelectric layers. Bonding materials include silicone adhesives, PDMS, epoxy, conductive glues. Bond thickness controls strain transfer must be optimized. Okay. Coil integration. Copper coils capture magnetic flux range. Performance depends upon number of turns, core geometry, annealing orientation. Surface engineering. Surface reference is improved by laser texturing, sandblasting, and lithography. This increases contact area, enhances triboelectric output. Thin film integration. FPGA thin films deposited by sputtering PLD or MBE integrated onto flexible substrate used in microsensors. Latest research developments. Multi-field coupling. Hybrid systems show mechanical, magnetic, and electrical coupling. This allows multi-parameter sensing. Okay. Machine learning integration. AI algorithms analyze complex signals, predict mechanical failure, enable smart maintenance. Okay. Additive manufacturing advances. In this, LPBF printed FPGA combined with magnetic annealing enables complex 3D harvesters. Number 4, high field magnetic annealing. High field magnetic annealing increases magnetorestriction by 2 to 5 times, dramatically improve TENG performances. Okay. FEGA does not convert energy, it connects mechanics, magnetics, and electronics into a single smart mechanical system. That is why it plays a central role in next generation energy harvesters and zero power sensors. It was the conclusion of this topic, and now we will move on to the key applications of FEGA based hybrid systems. Before we move on to the advanced research directions, let us first clearly understand why are the sciences actually used. FEGA based hybrid systems are applied in many real world technologies. Autonomous industrial sensors that monitor machines without batteries. Number 2, wearable energy harvester. These are the devices that generate power from human motion. Number 3, we have smart infrastructure monitoring. It builds bridges, buildings, pipelines, and railways. Number 4, IoT networks and passive wireless nodes. It creates sensors that communicate without external power. Number 5, we have zero power accelerometers, motion sensors powered only by vibrations. Number 6, we have self-powered robotic skins. It creates artificial skins that feel pressure and movements. Okay. Number 7, we have smart tires and vehicle vibration detection, real-time road and vehicle condition monitoring. Number 8, we have spacecraft micro vibration harvesters, and it helps harvesting tiny vibrations in satellites. Number 9, we have biomedical motion monitors. It monitors joints, muscles, and rehabilitation motion. So this material is not theoretically, it is already entering real systems. Okay. In portion 4, advanced research directions, AI intersection, sustainability regulations, and research roadmap. In this portion, we will look beyond today's devices. We will see where FEGA research is going in the future, how artificial intelligence is involved, and how sustainability and regulations shape real deployment. Okay, this portion connects material science, manufacturing, artificial intelligence, sustainability, policy, and ethics. Advanced technical frontiers, materials, and processing. Additive manufacturing, LPBF of FEGA. Let us start with in manufacturing. Laser power bed fusion uses a layer to melt FEGA powder layer by layer. It enables complex 3D geometries. Recent progress show LPBF can now produce Fe81 GA19 with controlled grain structure, strong magnetorestriction. However, printing alone is not enough because why? Because LPBF creates residual stress, porosity, dendritic microstructures. Therefore, post-processing is essential. This includes hot isostatic pressing (HIP), stress relief annealing, recrystallization, magnetic or stress annealing. With optimized post-processing, printed FEGA parts can approach single crystal performance. Now, next we have high-field magnetic annealing. High field magnetic annealing. Let us talk about magnetic field annealing. In magnetic field annealing, we anneal FEGA while applying a strong DC magnetic field. This biases crystal growth, aligns favorable 100 orientations, promotes easily 90-degree domain rotation. Research show that magnetorestriction can increase by multiple times, coercivity decreases, and low field efficiency improves. Industrial reality. Industry uses sub-Tesla to 1 to 2 T fields. Labs may use 10 Tesla fields to extreme optimization. High field studies teach us how to design scalable industrial processes. Doping and microalloying strategies. Another exciting research direction is microalloying. Small additions such as boron, carbon, and platinum can distort the latest modified defects, improve domain motion. For example, boron doping in LPBF FEGA increases dislocation density after annealing, improves magnetostriction, improves mechanical stability. Nanoprecipitates as controlled pinning centers improve reversible domain motion, reduce energy losses. Okay. Next, we have thin films and NEMs integration. At very small scales, things behave differently. Ultra thin FEGA films less than 100 nanometer experience substrate clamping, have strain gradients, show modified magnetostriction. Solutions include controlled epitaxy, smart substrate selection, patterned mechanical release. This enables MEMS harvesters, microactuators, one chip zero power sensors. New research also explores magnetoacoustic magnonic effects. Okay. Now, next we have hybridization strategies for TNGs. Why hybridization is needed? No single energy harvesting mechanism is perfect. TNGs, high voltage, low current electromagnetic harvesters need motion and magnets. Magnetorestrictive harvesters need strain. Hybrid systems combine straight. Okay. Magnetostrictive harvesters need strain. Hybrid systems combine strength. FEGA plus TENG capture both. It captures both surface charge and strain energy, increase bandwidth, improve reliability. Okay. Hybrid. Next we have hybrid topologies and benefits. Example includes layered bending hybrids. It better contact mechanics, simultaneous triboelectric and magnetorestrictive output. Cantilever hybrids with coils, fast TENG pulses, charge capacitors, slow FPGA signals, power electronics. Multi-modal arrays harvest energy from many directions, provide redundancy for sensor networks. Experimental show multiple fold improvements in output and duty cycle. Next we have artificial intelligence integration. AI for materials discovery. AI models predict curie temperature, predict magnetostriction, optimize composition and processing. Techniques include machine learning, graph neural networks, Bayesian optimization, DFT plus AI pipelines. This saves years of trial and error, identifies non-obvious dopants. AI for device design. At the device level, ML reduces expensive simulations, optimizes cantilever geometry, coil design, power electronics. Reinforcement learning dynamically tunes harvesters in real environments. AI for signal processing. AI for signal processing. Hybrid sensors produce complex signals. Edge AI, tiny ML, classifies vibration patterns, detects failures, reduces data transmission. This saves energy, improves network lifetime. Okay. SDG alignment and sustainability. Sustainable Developmental Goals (SDGs). FEGA hybrid. FEGA hybrid system support SDG 7, SDG 9, SDG 11 and 13. SDG 7 clean energy via harvesting energy. SDG 9 innovation through AM and AI. SDG 11 and 13 smart cities and climate resilience. Environmental considerations. Advantages: no rare earth dependence, recyclable FEGA alloys. Challenges: gallium supply must be managed, closed loop recycling is recommended, life cycle assessment required before large scale deployment. Limitations and risks. Okay. Bandwidth constraints. Magnetodestructive harvesters are resonant. Real world vibrations are random, and its solution is to hybridization, non-linear designs, multi-stage harvesters. Okay. Degradation and fatigue. Risk include mechanical fatigue, corrosion, GA segregation. Solution is to protective coatings, conservative stress limits, long-term testing 10 is to power 7 to 10 is to power 9 cycles, manufacturing variability. Challenges are porosity in aim parts, segregation in cast parts. Solution is to strong QC pipelines. Okay. ICP, XRF, EBST, CT scanning, magnetodestruction testing. Next part is power electronics challenging. Hybrid outputs are difficult to manage. High voltage TENG pulses, low voltage magnetodestructive signals, required specialized rectifiers, ultra low leakage circuits, adaptive switching. Now, regulatory and ethical considerations are EMC and safety. Devices must meet electromagnetic emission limits, follow wireless regulations. EMC testing is mandatory. Data privacy. Zero power sensors may collect sensitive data. Solutions on device encryption, edge processing, and ethical deployment policies. Occupational safety. For occupational safety, handling GA powders requires PPE, ventilation, safe disposal plans. Research roadmap. Near term 0 to 18 months, standardize LPBF parameters, publish open reference designs, establish QC benchmarks. Mid-term 18 to 48 months, guided dopant discovery, pilot infrastructure deployments, autonomous sensor networks. Long-term 48 to 84 months, industry standards, closed loop GA recycling, commercial scale production. Okay, now to conclude, FEGA stands at the intersection of material science, manufacturing, AI, and stability. Additive manufacturing enables complex designs. Hybrid TENG integration enables zero power sensing. AI accelerates discovery and optimization. Stability and regulation guide real deployment. The future of FEGA lies in interdisciplinary collaborations, and that is where our research generations come in. Okay. Thank you so much. This was all about my presentation.